Smart project.
Great.
Building design, report analysis. I designed a hockey rink. It includes 10 columns, 590 meter squared room, about 14 meters tall. It has a truss. It has 3 sets of layouts of beams, and by that I mean the front wall has a type of beam, the back wall is a different type, and the sides use joists, which is a different type. I'm just going to walk you through my report, pretty much. So, started off the project looking for a design. I wanted something reasonable where you could fire the puck up in the air and you wouldn't hit a roof, but I didn't want the walls to be too high, make it unmanageable, so decided to go with a truss. To scale scale the life-size arena down in AutoCAD. That's great. So moving on to the truss here, we've got. When I first designed this, I decided to only go with a very simple truss, which is this. There's 2 0-force members. Clearly not enough, too easy. You saw it in a triangle. I also did it wrong, I had to redo it. Decided to go with something more like this. Now, right off the bat, I'm going to show you, this is the front of the building. Right here is the beam. Excuse me, this is the beam on the front of the building, it goes across. I did not include the door in this design because it's only supposed to be showing the truss and the beam, which is the main components of it. So again, this is the front with the beam. It's the front with the beam. Beams across. These are made of wood. Everything on the inside is 4x4s. This is an I-beam. These are the columns on the sides. 5 columns on each side, makes 10 columns in total. All made of brick. Not all. The columns are made of brick. The rest of the stuff's made of wood. 4x4s mostly. So, yep. Got to the 4x4s, got to that, top of the truss. Yeah, so the beams. I used 3 sets of beams. Like I said, this is the back wall. Okay. So, this is the back wall. 1, 2, 3. Splitting it up into 4-meter areas, 4 of them, 7.5 meters tall. Sharing the load with the columns on the sides. They're perfectly even, so I'm going to solve one of them for tributary area, which I later used to solve deflection, shear stresses, and bending stresses. This is the side with the joists. These are all joists. There is 19 joists in total. They span 7.5 meters apart, and between each joist there is about 420 millimeters of room between each one. They don't cover the entire wall because the truss is very thick at the top and it covers about that much, about 1 meter, along with the I-beam and the rest of it. Yep. Sides and the joists. The back wall, which I showed you already, never mind. It's all 2x4s, these are all 2x4s as well. So the loading factors, well, let's just move on to that here. So SLS and ULS for roof. I had live load, dead load, snow load, wind load for the roof. That's twice as many for the floor, which gave me 7.4 kPa as a ULS. SLS was 7, adding them up. I'm going to go into this a bit more in the Excel. The floor is made of solid concrete, MD concrete. Gave me 10.875 ULS using a case 2, which favors the live load. Case 3 was used for the roof, which I didn't mention, which it favors the snow load. This favors the live load and the dead load. Awesome. So if we go into this Excel here, I can only solve for the beams on the sides of the buildings. So this is the front of the building. We have the deflection. This is the deflection max, and this is the deflection that I designed it with, that LO 240. So well within range. 2-meter beam, here's the base, here's the height, here's your I value, shear at center, and MMax, these are all found from Design Aid 6. Then I plug these in. This is all cross-sectional area stuff down here, which is, B equals whatever, VQ over IB is shear stress, or lambda. This is an MPA's, Newton millimeters, bending stress, all over here. It's all in Excel. It's all great. deflection for the back wall of the building. Here, before I used 4x4s for the other one. This one uses 2x4s. Exact same design layout. Here I've got 16 to 8, left enough room, well, more than enough room for deflection. Same stuff. Pretty neat to be able to do this stuff in Excel, I guess. It's really just plugging equations in, but. And again, 2x4s for the joists on the side of the building. Here I left, double enough deflection. I could have used 2x2s probably, because I left so little room between each one. Only 400 millimeters split between 19 of them, and 7-meter trim widths, which is actually I used a 0.02. Shear stress is 0.20. I feel like this is low, but then again, I just wrote quiz 3 for mechanics, and I got like 280 times 10 to the 17 for those on the test. So down here, I'm going to show you the load transfers through the building, through the truss. I specified the truss because this was sort of the the most difficult part. The beams, the load transfers are all linear. I could have done it, but it almost would have been a waste of time because nothing's happening on angles. I don't need to actually use any trigonometry, sine functions, or anything. All I have to do is draw it out. Kind of sucks. So I didn't do that. What I decided to do was design something more like this between all of the members, showing that, in fact, all of them except for 2 are in compression. This is in tension right here, and this is in tension. Weird, eh? Cool. Awesome. So this is that's my hockey arena design. Some last little notes. Conclusion. It was a lot of fun. The ice pad's 390 meters squared, and the entire building is 590. So the ice actually makes up for 66% of the entire building, which I thought was really neat, because that, let alone does that leave a lot of room for tying your skates over here, and penalty boxes. You could throw a bathroom in, maybe one of the corners or whatever. 4 entrances to the ice, 1 main exit, like a 7-meter door. It's huge. The boards are 2.5 meters. The glass is 2.5 meters tall around the sides. The glass is, and it's to stop the pucks from going out, really. Which obviously, and I made the boards really short, and the glass is only behind the net, by the way. Because I made the boards really short on either side, so you can dump people over them when they think they can get on breakaways and stuff. You just throw someone right into the penalty box, big time hip checks, damn, sniping silly. So 5 columns, multiple types of beams, beam layouts, joists, single-sided beams, above doors, tributary areas, all that good stuff. That's my project. Thanks.